What can we learn from nature to design urban transport systems? Today I'd like to share a concept study we did back in the days with phi360. It perfectly outlines how we use the power of an expert swarm and best practices to solve innovation challenges.
In order to do that, we assembled a team of experts from transit management, architecture, and ourselves as innovation managers. This is the way how all our projects at phi360 and Cobiom are approached. We not only get that inspiration from nature, but also from other analogous technologies. The goal was to come up with a urban transport system that serves the need of megacities and addresses not only the redesign of vehicles, but the complete concept of mobility at large that serves people and business at the same time, and in this way serves the needs that our economy and society have, but also the environmental issues.
The start point of this case study was Berlin, and especially here Tegel Airport, which we know is supposed to close down as soon as we eventually happen to open up our new airport. And this former Tegel Airport will then take space or give space for a huge technology and future park where new urban solutions can be piloted, tested, and developed. Now, the problem of this Urban Tech Republic, what it's called, field, the now Tegel Airport, is that as soon as Tegel doesn't serve as an airport anymore, the bus lines will be cut, so there's no public transport going directly to the public field. Now, the distance from there to the main city center, to the Alexanderplatz, is about 8 kilometers. Now the question is, how can we sustainably connect this area to the city center in a very modern, sustainable, and systemic approach? For that, we started already with a systems approach, looking into biological systems. And very interestingly, Berlin is not a city like many cities which has one city center, and from there, from a very central point, everything goes peripherally to the outside. Berlin is a little bit different. Berlin is a polycentric city, so it grew together from many different smaller cities, and therefore it has a very special character. So we thought this is not a unique approach, maybe for city planning, for urban planning, but not for biological or living systems. Because there we always have something that spreads, that sprawls, that distributes into the periphery, into modular systems. So that was the starting point. How can we start from an area like the now Tegel Airport and connect to many different centers? And this is what we wanted to do. So we wanted to have a point to field approach. Think of it like as if you have like your vein, your artery system, your blood system, where you have big arteries and they serve and provide nutrients to many areas, distributed over your whole body. So it basically splits off and you have a network of vessels at the end of your organs and your skin. So this is exactly the approach we wanted to take. We didn't only take an approach from biology, but we also used, and that again is on a meta level thinking in biomimicry terms, we tried to piggyback on or to leverage already existing both technologies but also approaches. And this is where Schindler came in with their port technology. The port technology was something that was developed to really solve the problem of elevators, where you, and probably most of you know that, you go into an elevator, you go inside the cabin, you press a button corresponding to the floor you want to go, and then you watch 5-6 people leaving earlier floors. So this is, on a user experience level, not very satisfying, because you're always stopping until you eventually reach your floor. What Schindler did was introducing the port technology, which is a terminal outside the elevator. And that makes, of course, sense, especially in high rises where you have during peak hours a lot of people traveling with these vehicles, because here we're talking about vertical transport. And those people then enter their final destination into the terminal, and then based on an algorithm, the best vehicle, the best elevator is allocated to a group of people, minimizing the amount of times that people have to stop before they reach their final destination. This is called destination control, and that is something we wanted to bring into the horizontal mobility landscape by rolling this out into urban mobility. What this already does, and this was one of our design requirements or our design guidelines, is that it connects individual and public transport. You have an individual destination, but you're pooled with others in an algorithmic way and transported in the most efficient way to your final destination. Now, the question then was also to consider urban mobility as an entire ecosystem, not just thinking about how can we improve the car, but really how can we rethink the way we do mobility today. And it was not only about looking at how can the car be reshaped, or how can we make it more efficient, or how can we think about alternative mechanisms like going from fuel consumption to electricity, but really thinking about what is the infrastructure these vehicles shall use. What is that vehicle actually? What's the size? What is the architecture? What is the functionality of all that system? And how does it interact with people? So at first we did an analysis of the city ecosystem in Berlin. And we were actually shocked when we looked at how city architecture is done today. It's really dominated by decades of car and traffic. So if you look at the street, you see that up to 70% of the space between houses is used for cars, either driving or standing. Then on average in Berlin, there's 1.3 people in a car, whereas it can, as we all know, fit 4 to 5 people. And then a car, during its lifetime, it's used about 5% of the time. 95% of the time, it's just standing still, an idling resource that is not used. And the craziest number we have found was that up to 2/3 of the traffic in the city center of Berlin during rush hour is traffic to look and search for a parking lot. This is mental. This is not sustainable. And we accept this on a systemic level. Any business model could not survive. Any biological system with these metrics would not survive. Yet we have an urban mobility system that operates like this today. So there's a huge room for improvement, and this was the starting point for our design approach. Now, if you look at public transport systems, for instance, and you compare it to a neuron, which is one of the most efficient cells when it comes to communicating and transporting things and moving information across, then you see striking similarities in architecture. Now, our idea and looking here into a biomimetic approach was how can we learn from these systems and how can we leverage this for mobility options in the 21st century. And if you look into mobility and cells, and this is not exclusive to brain cells or nerve cells, you find this equally in other cells, like in those fibroblasts, which are skin cells here, you see that again, like in a human-made city system, you find highways or roads or mobility infrastructures. These are highlighted in green here. And then there are others which we could highlight in other colors. So we have different kind of infrastructures, just like we have in the city. Subway, road, pedestrian way, and so on. And then you have different vehicles that move along these infrastructures and different cargo that needs to be transported. So the question we had is, how does it work in biological terms? So we looked into this in more detail. We spoke and worked with experts in that field, molecular transport within cells, and we realized that there are different components. There's infrastructure, like microtubules. There is cargo that needs to be transported, like vesicles. And there are vehicles, like motor proteins, that transport that cargo along a given infrastructure. Now, for us, it was interesting, how does this switch between infrastructures work? And here we basically looked into the molecular mechanisms and abstracted a concept that is about decoupling, both functionally and morphologically, that we then translated into a human problem-solving realm and looked into how can we redesign the car entirely, going away from this like 100-year-old typology of a car where we have a motor, 4 wheels, a passenger cabin, a trunk, and redesign around the people. If there is just 1.3 people on average in a car, why don't we build modules that are smaller? Why don't we build and design from inside out around the need of people Aerodynamics are negligible if we're driving with 50, 60 kilometers an hour in a city. So why don't we build smaller vehicles that allow for entire new functionalities and allow, for instance, for coupling to create larger units? Now that was the next design question we had. If we have a modular approach, if we have different smaller units that need to be coupled, how do we open and close certain entry points into this vehicle? How do we combine things in a modular fashion to bridge two opposite design requirements, one being stability, which often goes along with rigidity, and on the other hand, flexibility, which is almost the counterpart to stability, because very often things that are very flexible are not very strong. Now, we looked into a plethora of different biological models. Just to give you an impulse here and like some inspiration, we looked into the eye lens, the iris, how through different arrangements of muscles, the pupil can be open and closed. In terms of rigidity combined with flexibility, we, for instance, looked into mechanisms like the spine. The spinal cord and the spine, they are a great example of how one of our most vulnerable parts are protected by a structure that is both flexible and strong. Now, we looked into many systems, many principles, many functionalities to eventually abstract design patterns and mechanisms that we then put into use to design a new urban system for the 21st century city mobility. Now, what we eventually did was not only looking into certain shapes or functionalities in terms of coupling, but also on a meta level to think how can we move this system into a higher functionality, into more sustainability and better usability. So the first thing we used as a principle was modularization, looking into how can we couple different smaller units, because we know there is not 5 people on average using a car. How can we cluster smaller vehicles into larger ones? How can we then have a multi-functionality approach? We can not only couple different people, but how can we use the same vehicle for cargo and people? Because during off times, we don't need so many vehicles, even if it's a shared fleet. And that was another thing, leveraging existing resources and technologies. So how can we really not only develop new things, but really leverage things that are there, like cloud-based solution, a sharing economy model where we don't own the vehicle, but it's rather used as a big shared fleet, which allows much more flexibility and better resource use. And finally, thinking about the ecosystem approach and putting the user into the center. We've done a lot of user interviews, looking into what are use cases where we can use these kind of clustered vehicles to larger chains. How can this be used? Like, this could be an application for business meetings. You don't have to be in an office to meet people, to do a meeting. You could use a clustering on your way to work based on destination control algorithms, or an app-based, cloud-based system where you can match people based on certain functionalities. And this is where the destination control comes into place, because knowing where people want to go, where they're coming from, what interests or topics they share, you can bring them together, have a more efficient, in terms of energy efficient transportation, but also more user-friendly and a much higher experience in terms of transporting and mobility time for something else than driving yourself. It's needless to say that these vehicles are thought to be autonomously driving, and that leads me to another very interesting feature that we integrated, because it was not only about designing, or not at all really designing a fancy or nice looking thing at this point, but rather really looking into functionality. How can we make this work in a city? How can we make it work as a transition from current systems into the future, but also how can we use as much as possible existing infrastructures? So what we thought of doing was, why don't we hack? And this is where now this link, this hybrid between public and individual transport comes into play. How can we hack the public infrastructure that's in place with minimal changes in order to make that work? Now, the thing was here, through micro interventions, we could go into the underground, because we also figured, crunching the numbers, that 1/3 of the traffic is traffic below 3 kilometers in the city, but 2/3 of the traffic in terms of car traffic is more than 3 kilometers. We call this transit traffic. So if we could significantly reduce this transit traffic and move that maybe underground, everything that's beyond 3 kilometers in length, we call it basically not first and last mile, but everything in between, the transit transport. If we could move this underground, we have several advantages. The first being we free up space in the city environment, which we could reclaim for people, for parks, for living. We also can use an infrastructure that is safe for autonomous driving because subway infrastructure is built. It's at the moment not used at max, so we can use that for a much more sustainable and much more efficient functionality than just subways. We could use a charging infrastructure so that we have inductive charging underground and just with smaller battery packs, if we assume it would be electric mobility in the future, for the first and last mile. And eventually we could do all this matching and connecting and disconnecting underground and then disconnect the people again to go to their final destinations, having clustered transportation underground and longer chains, and then making transport more efficient, but also more effective, because eventually I bring the social component back into the equation because people meet based on common interests. So this was the system we were creating. Now the question was, how can we scale? So we thought, again, using existing infrastructures, and we identified the Siemens line, which was a former train line for the Siemens workers, which was destroyed in World War II, but large parts of it are still intact and not used currently. So if we could use and leverage this, similar to the High Line project in New York, we could create, again, an experience where we have a safe environment to test and run and showcase piloted and later autonomous driving, and connect cars, create an environment where people interact, where we make it immersive, where we make it really experiential, and eventually can scale from Tegel to the large city ecosystem and really have this point-to-field approach that we were starting with.
So this is the story of how we integrated modern technology with the lessons we learned from nature based on user research into a concept for modern urban technology. The vision was to go from something like this, from cities that are dominated by cars and by concrete and asphalt, to something that looks more like this, that looks and functions like a livable and desirable future, human-centered, integrating nature.